Hi, welcome back. So remember that we just finished studying ridge regression, which was a type of regularized regression. And there's going to be another type of regularized regression we're going to study, and that's called the lasso. So that's where we're going to start here. Let's check it out. Okay, so first recall that regularized regression aims to do these three things. It reduces the model complexity by shrinking the coefficients, theta 1, theta 2, that contribute to the target variable in 2 dimensions anyway. It converts an ill-conditioned problem into a well-conditioned problem. So we talked about that inverse x transpose x not existing, and then adding the regularization term will fix that problem. And then third, it reduces the dimension by feature selection. We haven't seen this yet because the ridge regression only does the first 2. Lasso, on the other hand, does all 3, and the price, as you will see, that we pay for doing all 3 is that we have to increase computational effort. Whereas the ridge had just a one-line solution. We had an analytic solution, a closed-form solution for the ridge regression. Lasso, you'll see that there is no closed-form solution. We have to solve the lasso problem iteratively using much more computational effort than with the ridge. Now, before we get to the details, LASSO, you should know, stands for Least Absolute Shrinkage and Selection Operator. You'll understand least absolute in a little bit, but you can already understand shrinkage. We're going to be reducing the model complexity. So those theta 1s and theta 2s and theta p's, they shrink towards 0 to decrease the model complexity. And this is going to be a selection operator, meaning that it accomplishes task 3 here. It reduces the dimension by feature selection. So that's the lasso. Now, before we get to the lasso, let's recall the ridge. What we said last time was that the sum squared error makes, I guess I'll write that as SSE. In 2 dimensions, the sum squared error makes this family of ellipses that I'm drawing here. And so the problem in ridge is to minimize the sum squared error. You know, the minimum sum squared error is like right here, right? There's the valley. That would be the ordinary least squares solution. But the ridge puts a regularization on that. It's minimizing the sum squared error subject to this constraint. And in 2 dimensions, we said that this constraint is a disk. And so the constraint is something like this. Okay, so we have to consider only solutions inside this disk where we choose the radius, which is the square root of t. And so with this picture that I've shown, the family of ellipses and the disk, the minimum here, it's not here, because then we can just walk closer down the valley, and it looks like the minimum would be somewhere around here. Okay, and so that would be the ridge regression solution. Theta r, or theta ridge, and where this one is the OLS solution, and we cannot find that because it's not in the area of allowed solutions because of the constraint here. Okay, now one thing we said was that we analyzed pretty closely what the role of lambda, or what the role of t alternatively plays in this minimization problem. And particularly we saw that as lambda goes up, thetas shrink towards 0. But we said an important point that when lambda is infinity, or when lambda is finite, the thetas will not be shrunk towards 0 at all. Okay, they won't be shrunk to exactly 0. Now, that's important. That's an important distinction to make, because sometimes you want to know exactly which features are contributing to your model and which are not. For example, if you had a measurement of diabetes progression, this is a famous data set. If you had some sort of measurement on diabetes and you were wondering which variables actually contribute to diabetes, And so from your diabetes patients, you measure some sort of measurement on how far along in diabetes they are, or how serious their case is. And then you also measure their age, their sex, maybe their body mass index, and then you measure maybe 5 blood serums. Okay? And the question is, which of these contribute to diabetes? Well, let's say for body mass index, you measure its corresponding theta to be, with regularized regression, with ridge regression, maybe you get theta to be 0.0001 or something like this. Okay, well, how close to 0 does this have to be where you say body mass index does not affect diabetes? We would like some way of actually shrinking these coefficients to exact 0. If we can shrink them towards exact 0, then we have accomplished point 3 here. We can reduce the dimension by just removing body mass index, and we've performed feature selection, essentially selecting the non-zero weights or the non-zero variables. Okay, so ridge regression cannot do that. And it's because actually it turns out of the curvature of our boundary. Lasso, on the other hand, has a diamond-shaped boundary. Okay? And so what happens here is that because of the diamond-shaped, it's very possible that the minimum occurs right there on this axis. And so what point is that on the axis? Well, that is some theta 1 comma 0, right? And so if the minimum happened exactly on that axis, we would say that feature 2 does not contribute at all to the model, right? So this is the idea behind Lasso. It's just a slight tweak to the minimization problem that we saw in Ridge that actually makes the decision boundary, or not the decision boundary, excuse me, the constraint a diamond, and that's what performs feature selection. Okay, so what's the equation in 2 dimensions? So this is theta 1, right? This is the length of theta 1, and this is the length of theta 2, right? What's the equation of a diamond in 2 dimensions? Feel free to pause the video, but it's this guy. The length of theta 1 plus the length of theta 2 is less than or equal to t. So less than or equal, so we can consider all of these solutions in here. Okay, that's the equation of a diamond. And so that's going to be the equation of our constraint. Okay, so we're going to adjust the minimization problem. We're going to say the lasso minimization, call this a JL for lasso, is going to be reduce the sum squared error, okay, which is this guy, plus lambda times, and then what we're going to do is not square, but just take the absolute value of each theta. Okay, and so that's going to be our penalization term. Or, written in that second form, okay, this is our minimization problem. We can also minimize the sum squared error, so the ellipses, subject to a constraint on the absolute values. Okay, and that's what we said over here. All right, so now we're actually going to make a little bit more sense of this by drawing this objective function in 2 dimensions. So I wonder what that might look like. And we already said that the sum squared error portion of this is an ellipse. So what does adding, this absolute value stuff look like? So let's investigate that a little bit. So we have to understand what this graph looks like if we're going to be able to solve that minimization problem. Okay, so I'll just draw two dimensions for right now, theta 1, theta 2. And it turns out that the plot of this in two dimensions are ellipses that come to a point. So it's kind of like this. It's like a deflated football. You Patriot fans, okay? So we have kind of these ellipses, these pointy ellipses, and the larger lambda is, the pointier these ellipses get. Okay, so we have something like this, and we have to solve this problem, right? We're going to have to find the minimum of that thing, the theta that minimizes that, and we wonder, how are we going to ever solve that? Well, graphically we can see that here's the minimum. Okay, we're going to try to get to that minimum. Right? And this is the way we're going to solve it. It turns out we can't use derivatives in two dimensions. Because, or more than one dimension, we can't use derivatives. And the reason we can't use derivatives is because of the absolute value. So the very thing that allows us to perform feature selection, which is the point, right, the absolute value, the diamond, the very thing that allows us to do feature selection keeps us from finding an analytic solution, because the behavior of the absolute value is not well defined for the derivative. So what we can do, though, it turns out, and we'll work our way through this in later videos, is that we're going to use an iterative algorithm called coordinate descent. I'll write that here. And what this means is that we're going to consider each coordinate system, or coordinate axis, separately, and we're going to descend on the minimum. So we're going to initialize our guess to the solution, maybe at 0, 0. And then we're going to choose one of the dimensions, maybe dimension 1, and we're just going to walk along that axis until, walk downhill until we start to walk uphill. So maybe that's about here. Then we're going to consider the second axis, axis 2, and we're going to walk this way, downhill, until we start walking back uphill, which is maybe right there. And then we're going to repeat, right? And if there was a third axis, we'd go through the third axis and so on. But now we go back to axis 1, and we go until we start walking uphill. It might be like that. Then downhill for axis 2. And we keep going, right, until we get to the minimum. That's how we're going to solve the problem. We're using the coordinate descent algorithm. So this algorithm in pseudocode looks like this. So step 0, first we're going to normalize. So this is an important point. We're going to normalize data x and y, okay, meaning center y. And then standardize, so use the z-score on x. We're going to initialize a guess. Okay, sometimes that guess, in two dimensions is 0, 0. Sometimes the guess is the ordinary least square solution. Then we're going to minimize in the theta 1 direction, minimize in the theta 2 direction, minimize, right? Minimize in theta 2. All right, and then we're just going to repeat that. And then we're going to stop when the solution does not change too much. I'll just write barely changes. So we can look at, for example, the fractional percentage, or it changed by less than 1% from the previous iteration, so then we'll stop. Okay, so that's kind of the introduction to Lasso. And so in the next video, we're going to start to be able to, figure out how it is we're going to solve this, nail down the details. All right, so let's check it out.